Thank you again. So indeed, today we'll be talking about AWS and secure authentication with certificates. If we take a look at embedded security first and foremost, it's a layer cake. It's a layered architecture that has basic practices that you want to consider implementing, depending on your product, of course. Start with hardware, we talk trust, which will be the very essence of today's presentation, and how we protect this trustable identity that needs to be protected. It all relies on the private key. Then you have counterfeit protection, IP protection, secure communication, secure updates, secure communications, and application layer. So at Microchip, we offer a variety of products from 32, 16-8-bit microcontroller, trusted with trusted execution environment or not. We got microprocessors, we got FPGA, network controller, whether they're wired or wireless, and that integrate communication stack. But today we're going to focus on secure elements. So let's start with another security statement. Security, it's all about the key, and there are two theorems from Kirchhoff and Shannon that says that crypto system should be secure if everything about the system except the key is public knowledge, and the enemy knows the system. You need to assume that. So what you want to do is protect your key first and foremost. So why is it important? Because if you possess the key, you can start impersonating, you could start impersonating transactions that are critical to the system. So think about a payment transaction, for example, or a confidential patient information and so forth. Those start to be problematic. So how do we protect the key in a traditional system there? We recommend the usage, and we've seen a huge uptake of usage of secure elements in IoT system. Because this device, what it is, it's a companion device that acts as a vault for the key to be protected in a connected system. So the way it will work, it will have the private key here inside the vault, and the private key is generated during the manufacturing inside the device, inside Microchip factories. The way it works with the microcontroller has something called cryptoactive library, which is a library that allows the microcontroller to be completely agnostic of the secure elements. The micro sends a challenge that will be signed by the private key using a crypto engine integrated in the secure element. And you do want the crypto engine in the same secure boundary as the key here within the secure element to ensure best protection. And the signature will be the response that will be then checked later on. That concept, when you go deeper and deeper and deeper into the transaction, it will be a fairly technical session. So what the secure element also brings, it helps to make sure the keys are not exposed at any point of time during the development, and especially the manufacturing phase of the product development. That's very important. I mean, you could be exposed to operators and test equipment running Linux and or network security in your factories, and there are other level of exposure that the secure elements eliminate or try to eliminate. The more you isolate the keys from people, operating systems, and equipment, the better off you'll be. So that's why that becomes a pretty interesting device. So what's inside the secure elements? You have a crypto accelerator, depending on the crypto curves that you want to use, which is still very high level right now. You could have the SHA algorithm, you could have the ECC P56 algorithm. You have a memory zone, a secure memory zone. That's where data and keys will be stored. You have a unique serial numbers. You can do some interesting things in your challenge response with serial numbers. You have monotonic counter if you want to monitor usage of that device. And you have, of course, a high quality random number generator that will be used to generate the keys there. All the devices equipped with tamper protection and side channel attack protection. What the side channel protection are helping with is basically reducing the surface of attack that relates to basically altering the basic voltage, temperature, current, and frequency. Those are the four variable that the side channel protection are trying to fight against.
Hey, Xavier, we actually have a question that came in, and I think this may be a good opportunity to address it. The question is, why is the secure element a standalone device?
Yeah, that's a good point. That's a good question. You know, like just I mentioned, the side channel attack protection are trying to protect against attacks that will try to alter the voltage, current, frequency, and temperature. So if you integrate this type of IP into a microcontroller, things becomes much more challenging and quite a bit more expensive, significantly more expensive. There are several reasons. So from a security standpoint, sharing the power lines, the clock lines that's where your vulnerability are going to be. And we've seen it in the market the countless time on larger microprocessors that are provided in the industry. If that's not enough justification or not clear enough, let's take the facts, right? Existing practice in the industry. You've got the world of servers. They're using TPM. TPM is a discrete secure key storage. You got the world of computers, a laptop are using a TPM. That's another discrete secure key storage. Credit cards. So you do have in your credit card a secure element. The keys from the rest of the system. On the phones, you have a SIM card. That's also where your keys are to authenticate your connection to your telcos. And all of that, you have another value on top of isolating physically that secure space for the key, specifically for the key from the rest of the system. You also have a logistic reason. So it's customization. You have a key, you have customization. You have customization, you have a supply chain problem, challenge. It's cost in the supply chain. So it's more cost effective to customize a tiny piece of your system, the secure element, versus handling a fully customized system that you're going to have to ship across the world. Much more cost efficient from that standpoint. That's why it's been a practice to use those discrete architecture. So the challenge remains, and I've hit on it, it's customization when you deal with security in general, not just secure element in general. It's customization and how do you scale a customized system across the globe. And before you scale across the globe, you have to go through the development hurdle. So that's what we've tried to address at Microchip and our secure element portfolio. We've launched the Trust platform, the Microchip Trust platform for the crypto authentication family. Comes with 3 variants, Trust and Go, TrustFLEX, and Custom. Trust and Go is kind of a black box where it comes by default with a pre-provisioned private key, and we offer certificate in the form of a manifest. TrustFLEX and Trust Go will do device to network authentication or that are IP-based or LoRa-based. TrustFLEX can do the same thing and more, and that's what we're going to talk about today. So I'm not going to expand too much on the use case. That's the next slide. Trust Custom is basically a fully customizable secure element. The cool thing is we wanted to make, the market wanted that technology at minimum reliable quantity MOQs that were very low. And we did that. We adapted our supply chain to go down to 10 units for Trust and Go, 2,000 units, and 4,000 units for Trust Custom. That includes the provisioning service. We have a high volume flow, so as soon as customers are reaching a certain threshold in their project and product becoming successful, we can flip them to a high volume flow. What that means is a better cost structure. So the TrustFLEX, what's inside? You can do certificate-based authentication, JSON Web Token authentication, secure boot with key attestation, OTA verification, firmware IP protection. So what this is really we're verifying firmware at different point of time of the system operation. Message encryption. You could do key rotation. We have that questions. So we have the question quite a bit. The answer is there, but to be honest, we rarely see it used because it has consequences in the backend infrastructure that are pretty complex to handle and to be expensive. IO protection, what it is, it's the capability to pair uniquely the microcontroller and the secure elements. And we could, the TrustFLEX will also handle the host accessory authentications. Quite a few use cases. You can use one or all of them. It doesn't matter. It's available for you to use here. If you want more information about the device, you can go directly to microchip.com/TrustFLEX. and you'll see all the details being explained here.
Hey, Xavier, you've described all the features of TrustFLEX, but can you walk the audience through the benefits next?
Yeah, absolutely. So yeah, that was the what's inside, and looks like we prepared for it. The benefits are right there. So the fact that what we used there was all the most commonly used use cases in the industry that we've seen for the past few years. So the device is first flexible. You can support any type of microcontroller core, microprocessor cores. Those are the cryptoaffib. It can connect to any cloud platform as long as you have a TLS or a LoRa network. It's completely fine. It can accommodate any certificate authority. It's all depending on the choice of the customer certificate authority. We supported pretty high volume of customer accounts, and we're pretty confident our system is flexible to at least all the most popular certificate authority providers. And it allows the customer to use their own secret right at the end. That's something you couldn't do with the Trust and Go because you have to use the default credentials Microchip offers there. From a time-to-market standpoint, obviously, we've been baking in all those predefined use cases inside to avoid engineering time to be spent on basics. So we've configured the memory zone with the use cases that I've enumerated before, and that's actually the part of a good chunk of time where engineering is being spent. Try to understand and learn. There's a huge learning curve. So we have been helping to fast track that development phase by baking in those use cases that I've talked about. The low MOQ enables the technology to be available for any type of project size. It doesn't matter the company size, it matters for the project size. It could be a small project, a large company, a small company launching a low volumes that wants to benefit from this technology. And then we simplify the engagement model with the Trust Platform Design Suite software that I'm going to illustrate at the end of the presentation. Today, I'm going to focus specifically on the AWS just-in-time registration implementation and how do we leverage the TrustFLEX ATECC608 within this environment. So let's go through a few basics. The certificate-based authentication is what we're going to talk about using X.509 certificates. So what it is at a high level, it ensures authorized connection are allowed to the cloud platform. So in this case, AWS IoT. It validates two things, the product to the cloud and the cloud to the product. That's your mutual authentication. And all of that is done through a TLS, a transport layer security, that brings encryption of the connection and helps to ensure private communication of data. You need to prove your identity before you push data. If you push data, even if the data are encrypted, they're going to land somewhere that you can't trust if you haven't proven the trust. This is authentication. You prove your identity, that your identity is trusted, then you can push information to that identified edge node. That's a step further in the world of certificate. The way it looks like, it's a hierarchy, right? So you have your main certificate. So in the real world, we'll talk about root certificate authorities. They all are not there. Sometimes they are skipped, and we see customers using directly call that the customer ecosystem certificate. The names are intermediate certificates. That's on the customer side. So it depends on how they are handling their own architecture on their side. Once it comes down to the device, what we do with the clients, we do a secret exchange for the customer to allow us to generate signer certificates and device certificates on their behalf, attached to that chain, to their chain of certificates. So now we start to create that link between the customer and the device themselves. It's using P256 elliptical curve, and it's DSI with SHA-256 algorithm. That's a very optimized algorithm from a processing speed standpoint and from a memory footprint standpoint. So that's been the algorithm that has been more than emerging, dominating the marketplace today. From an AWS IoT use case, we take that certificate chain that I illustrated before. The customer will, initiate their customer certificate. Either they start from a root certificate authority, or they start directly at the customer certificates, either or. We've seen both cases. Doesn't really matter, because for us at Microchip, what we want to do is to create production signers, and that's what's happening. There is a secret exchange with Microchip to allow certificate generation on the customer behalf, and that's what I was mentioning just a minute ago. So we then, once we have a certificate signing request with the client that allows that being signed, and that's where we manufacture the production signers. Production signers are uploaded by the clients, by the customers into their AWS account using the Bring Your Own Certificates feature here. Then also within the Microchip environment, we provide the last layer of certificates we call device certificates. And both the signers and the device certificates will be inside the secure element here. The certificates are not yet uploaded. They do need to exist in the AWS account. So how does that work? The way it works is at the first TLS connection, the device will be pulled into the AWS account and verified by the signer account. So now you can see from a logistics standpoint how elegant the solution is. You don't have to carry around your device level certificates from CM to CM and whatnot. From a logistics standpoint, furthermore, what that means, imagine this is a box, this is your secure element. What Microchip needs is a dropship address with your contract manufacturer, and we'll drop those pre-provisioned, pre-configured devices at your CM. So it allows you to continue business as usual with your CM and keep a very optimized throughput in your supply chain, because you eliminated a chunk of the customization due to the uniqueness of the keys into a system. That's offloaded to Microchip into our secure elements. You will give this customized secure element to the CM that doesn't have to deal with keys. So from a security standpoint, is isolated from the keys. And from a logistics standpoint, just grab a part, solder it, and the code on the microcontroller is always the same. Very efficient. At the end, the customer has a customized part number, and that's how the device itself is attributed to the customer in a unique manner. All the handling is obviously of the keys and the certificates is done within Microchip secure factories, where we are equipped with hardware secure module HSMs here. So let's go down to, so that was a high-level concept from the clouds, the provisioning, and the clients. Let's take a look at what's happening at the code level. So that's how the code would be architected, where we have the cloud, the host microcontroller, and the secure element itself. Like I said, inside the secure element, you remember the last animation, we have the signer certificates, the device certificates, and the private keys that will sign something. What the cloud will do, it will try to verify things, and it will try to ask for proof of identity. And that's what's happening. So we're going to break it down in two phases. First, we need to verify the certificate chain. So what's happening here, the device, the secure element that has the secure element will present the signature and the public key of the signer to get it verified by the OEM public key or the customer public key that will be in the, waiting in the cloud. Remember, the customer has loaded his own certificates first and foremost in his cloud account. You get this first verification. Second level of verification is the device certificate level. So same thing, we present the device, the public key, and the signature. That both will be verified by the public key of the signer itself. So we verified the certificate chain. Now we need to prove the identity of the device, and we need to verify the ownership of the private key. Who owns the private key, and can I trust you? So what the cloud will do, it'll send a random challenge that will be signed with an CDSS sign that will then be verified with the public key of the device, with the device public key. Once that session is complete, we close the authentication, and now we can push data safely. If you think about it further, now with the emergence of artificial intelligence concept, models of data, right? Can you trust your AI model if you can't trust your authenticated system? So your investment in AI should consider implementing a trusted authentication. And there are many other use cases like that. So what are those X.509 certificates and how they're handled? what's happening here at the microcontroller level, we are compressing certificates in the 608. You've got the certificates of composed of static data and dynamic data. What the secure element will do, it's handling only the dynamic data, the information that change from one certificate to the other. Why do we do that? Again, we try to keep the system optimized, and yet by providing a pretty good level of security here. So it's efficient. It provides an efficient use of the non-volatile memory space on the 608, because the only piece of the certificate that are being 608 are the dynamic data. So meaning your memory footprint doesn't have to be humongous. We've seen that question where, hey, I want all my 16 keys into, I want 60 keys into the device. Okay, what are you doing with it? And then you understand they're trying to do way too many things. If you concentrate to the dynamic portion of the data, of the certificates, your code infrastructure and your embedded architecture become pretty optimized. How is that possible? Again, remember I mentioned CryptoAuth is the library that helps you construct the X.509. I think we have a question, Meg.
Yeah, I was about to address that. You talked quite a bit about certificates. Can you explain what's actually happening to those certificates?
Yeah, absolutely. So that's what CryptoAuth helps with. So that's certificates. You have all the fields of the certificates, and what CryptoAuth will be doing, that lives in the host microcontroller here, and the secure element is your discrete device here. It will basically split the certificate here, the dynamic data of the certificate, and that's what really is handled by the within the secure element, the public key and the signature. And that's why you can see from memory space, you don't need to have a ton of memory into your secure element to handle a basic secure authentication to your cloud. So how do we start with this whole thing? We've got 7 more minutes. I'm going to show you. I'm not going to run and execute code right now, but I'm going to show you tools and how they look like. I'm going to guide you through the steps that you should be able to take to complete and implement this solution. We'll probably do we'll probably re-record the session where I will have time to execute the code, and we'll format the video a little bit better. The first and foremost, you start with your hardware. So your hardware, that's your base board here, that BM320118. It has the variants of TrustFLEX, Trust and Go, TrustFLEX, and Trust Custom right here. It has a Cortex M0, and it has a microbus port where you can basically work with more secure elements if you lock a TrustFLEX or lock a Trust Custom by mistake, for example. So you can have that board with soldered down parts. Again, you have, I think, 2 Trust and Go, 3 TrustFLEX, another 2 Trust Custom, I think, that's how it's set up. You can snap it on that board to have more secure elements. We have sockets, both for the Explain Pro form factors or the Microbus form factor here. So this one you'll have to get it directly from Microelectronica. And we'll need to work with a Wing1500 Wi-Fi. I'm going to show in a minute where it's at and how to get it. The flow for the tool is that this is what helps with the onboarding. So we created a software that's called the Trust Platform Design Suite. The first thing it'll do, it'll help you to map the use case to the configuration you want. So basically, you see use cases here. You're going to select, and you'll see the magic happening. Basically, the code is going to, the configuration is going to start to show. I'll show the tool in a minute. Then we have Python executable tutorials that will run from your laptop and talk directly from the laptop to the secure element to test the config of your secure element and the credential you put there are working. Then we also wanted to provide you with C-code projects, turnkey projects, especially for the AWS IoT mutual authentication. That's what I'm going to show. We also provide the C-code projects of the equivalent use case. And then we provide a utility that helps generate the secret exchange file that you'll need to provide to Microchip provisioning service. So I'm going to switch out of the PowerPoint and show you what I'm talking about. So the first thing you want to do is go to our website here, go to the Trust platform. You'll select the TrustFLEX. As you can see, I printed all the page here. On the TrustFLEX page, what you'll want to look for is install the Trust Platform Design Suite. Again, you get more explanation about use cases and so forth on the web. The tool that I was mentioning is the DM32018, and you do want to have this Wi-Fi click 7. It will be important for the manipulations here. So then the tutorial for the installation is pretty well described step by step. I'm not going to go through that today. It takes some time to install. You'll see we have a UI that's pretty elegant, and I'll help you also to clone the GitHub repo by just following this procedure without being an expert. So follow the manual. It's there for to serve you. The solution works both on Mac and Microsoft. Make sure you get the right versions too. What else can I tell you about it? So that's the Wi-Fi, the way it looks like from Microchip. Go get it. You'll need it. Make sure you update it to the latest firmware. And then once you launch the GUI there, what will show up is something basically like this here. So it will present basically kind of the web. What you'll want to go to is directly to the TrustFLEX section here. TrustFLEX will take you to this, and that's where the interesting piece is. That's where you select your use cases. You could do X, Y, depending on what you want to do. Here we're going to focus on the public key infrastructure. And what will happen will show up the transaction diagram between the micro and the secure element and the cloud with all the command of the library. But what's really cool here is the configuration is highlighting the slots that will be actually solicited during the manipulation. If you click on the slots, you'll be able to decide if you want a custom certificate or use the Microchip certificate. And at the end, this is where you click generate the provisioning package, and it's basically generating the file like our provisioning service is expecting it to be. So from there, you'll get into the Python executable environments running on Jupyter from Anaconda. Taking big shortcuts. Once you launch, again, follow the manual and you'll get there. I'm going to show you the interface. What we'll be launching are those IPYNB files. Those are Jupyter notebooks. The way it looks is like this. The first thing you want to do is create that certificate chain. And this Python code is prototyping a certificate chain for you to start prototyping. You don't want to use that certificate chain for production at all. So that's once you have your credential, what you'll be doing, the tool will also help to provision them into the board that we showed there. And it takes literally less than a minute. You run the executable, it loads automatically the credentials into your and you're done. You're ready to, if you want to stop at the secure element level, you're done. What we also provided was with our MP Lab environment, we provided actually a turnkey project, a custom PKI AWS project. And once you've loaded the credential, you have to follow the whole procedure. We'll have a detailed video on the topic. The only thing you'll have to do there is to change your password and login and password on your Wi-Fi. You'll have to access the endpoints that's in your AWS IoT accounts. I'll show where to get it from to get you guys a visual. Let me pull up my HTML. So if I'm in the AWS environment, so I'm on the AWS website, I'm going to look for AWS, IoT core. So I've created everything. I've run that manipulation several times, but I want to show you a visual of where to get your endpoints. I want to go to secure my certificates. So remember, when we run the notebook, it also uploaded the certificates for me inside my accounts. If I click on my certificate, things, click on my thing, interact, and that's where your endpoint here. So this is what you will want in your code. You execute the code, and you should see the communication happening. And for the sake of time, we couldn't execute all the code there, but we want to give you a visual of what to expect with the tool. You've seen the Python executable that generate the certs. There is a second one, actually, I forgot to show, that shows how to, that helps you to upload your database accounts. You got the C project, and this is what we were reflecting here. I'll finish here. I know I'm 1 minute after. So the process when you want to go to production, so you use this design suites within the TrustFLEX notebook that I've showed. You've seen where the button is to start triggering the secret exchange. You load that into microchip.com/support, you create a ticket, and then that's when the magic happens. So you upload your file, and what we'll create at Microchip are provision secure elements with the keys that will ship directly to the location you want us to do. So for us, what we need is a dropship address. We'll get the secure elements, including the keys you wanted us to provision. And that entire structure is available through, we made this infrastructure flexible to be leveraged by our distribution partners. It's also flexible by being capable of working on any cloud, any PKI, and it adds a lot of security use cases. So that's what we wanted to go through with you guys today. The whole idea here is to simplify everybody's life and make this security technology more easily accessible to customers, no matter the size of the project they're handling, by keeping the entire thing agnostic of cloud, PKI, controllers, and connectivity. Thank you for today's session. Megan, if you want to wrap up the session, it's all yours.
Yeah, absolutely. Thank you, everyone, for joining us today. We hope you found this session informative. Be sure to visit www.microchip.com/shields-up to view all upcoming sessions and watch past presentations on demand. Please follow us on LinkedIn, Facebook, Twitter, Instagram, and YouTube for the latest news and updates. Thanks again for your time, and we hope to see you during our next sessions, and have a great rest of your day.